In our last class, we said that in all points of space in the universe, there is a magnetic field, just like there is an electric field. We call that magnetic field B, and it is a vector field, so at every point there's a magnitude and a direction of this magnetic field. The units are in Tesla, which ends up being Newton seconds per Coulomb meter, but we just call that a Tesla. We can draw diagrams and depict magnetic fields using magnetic field lines, which go in the direction, is a continuous line that goes in the direction of the magnetic field, and the strength of the magnetic field is indicated by how many lines in a particular area there are. So the more densely packed the lines are, the stronger the magnetic field. We looked at the magnetic field created by a bar magnet. The lines come out of the north and go around and come into the south on either side. Strong near the two poles, near the two ends, weak along the sides, and of course weak if you're far away as well. Also, the magnetic field created by a wire that's carrying current. Concentric circles going around. Stronger when you're close to the wire, not as strong when you're further away from the wire. The Earth is a big magnet, kind of like a bar magnet, and here were the field lines depicted. Right around the surface of the Earth, where most people live, the strength of the magnetic field is a little less than like 10 to the minus 4 Tesla, something like that. Okay, and then we started talking about what that magnetic field does. And what it does is it exerts a force on any particle that has a charge and is moving. Okay, so if you don't have a charge, you're not going to feel a magnetic force, and if you're not moving, you're not going to feel a magnetic force. The magnitude was given by this formula. The magnitude is QVB times sine of theta. So just to go over this again, Q is the charge of the particle, V is its speed, B is the strength of the magnetic field, and then sine theta, theta is the angle between the speed, the velocity vector, so the direction that the particle is moving, and the direction of the magnetic field itself. So again, that also can be zero if the particle is moving with the field, either in the direction of the field or actually going against the field. The angle would be nothing, it would be zero, and then this would be zero. If you're going perpendicular to the field, sine of 90 degrees is 1. And anything in between, sine of that angle will be between 0 and 1. So that's the magnitude. The direction of the resulting force, magnetic force, is always in the third dimension. So if the V and the B together sort of define a plane, a 2 dimensions, the magnetic force is always going to be sort of perpendicular to that. So it's going to be perpendicular to the V vector and perpendicular to the B vector, according to the right-hand rule. And again, the right-hand rule is use your right hand, arrange your right hand so that you can curl your fingers from the V to the B. And if you're holding your hand where you can do that comfortably, then your thumb sticking out to the side of your hand will be pointing in the direction of the force. So if you do that here, V to B, the force will actually be going into the screen. So this object currently moving this way will feel a force pushing it inward into the screen. Which means, of course, that it will accelerate that way if there are no other forces, and so it will actually not be moving exactly this way in just a second. Now, because we absolutely have to use 3 dimensions when we're talking about magnetic force, I want to establish a couple of conventions. So obviously, if we have any vectors going sort of, in the plane of the paper or screen that we're writing on, we can draw the vectors as we always have. But now we are going to often be dealing with vectors that are going into the screen or your paper or coming out of the screen or your paper. And so how do we draw that? rather than trying to draw 3D pictures in perspective or anything like that, what we're going to do is we're going to use the following convention. An X will mean into the screen or into your paper. And a dot will mean coming out of the screen. And the way to remember this, or the way to think about it, is it's kind of like an arrow, like an actual physical arrow. If an arrow is coming right at you, the thing that's closest to you will just be the point of the arrow. So this is like the point of the arrow coming right at you. Whereas if the arrow is going away from you, it's like the feather, the cross-hatching feather part in the back. You'll kind of see an X. That's what you'll see if the arrow is going away from you. So that's kind of the thought process behind these two conventions. Okay, so we'll use that going forward. So let's try this problem. A magnetic field of magnitude 2 Tesla, 2.0 Tesla, which is a very, very strong magnetic field, is directed out of the screen toward you. At a certain moment, a proton is moving horizontally to the right with velocity 4.0 times 10 to the 6th meters per second. Find the force on the proton and its resulting acceleration. Okay, so I want to draw a magnetic field, a nice uniform magnetic field, directed out of the screen toward us. So those are dots. So I'm just going to sort of put a bunch of equally spaced dots. The equal spacing, right? Remember that magnetic field lines are, the strength of the magnetic field is indicated by the density. So I want them to be sort of equally spaced so that it's the same density throughout. So just a uniformly strong 2.0 Tesla field. All right, so these are, picture a bunch of field lines, a bunch of arrows coming at you. That's the magnetic field. And we have a little proton, which right now is going this way at our given speed of 4 times 10 to the 6th meters per second. So we want to find the force on the proton and its resulting acceleration. Now, when we say force, we want the magnitude, but we also want to say what the direction is. Okay, so first the magnitude. FB is, so it's QVB sine theta. Okay, so for a proton, that's our 1.60 times 10 to the minus 19 coulombs, positive, times our velocity, 4.0 times 10 to the 6th meters per second, times our magnetic field of 2 Tesla, times the sine of, now what's the angle? What's the angle between the V and the magnetic field? Well, the V is going to the right and the magnetic field is coming straight out. So that's actually a 90-degree angle. And the sine of 90 degrees is 1. So basically the sine factor is just going to be 1 here. Okay, so this ends up being 1.28 times 10 to the 12th newtons. That'll be the strength of the force that this proton feels. Now, what direction is it? Okay, so it's a little hard in the video because you can't see me doing it with my hand, but we did this in the last class. You want to arrange your hand, your right hand. First of all, point your fingers so that they're going to the right, but then rotate your hand so that then you can comfortably bend your fingers so that they're pointing sort of out as if they're coming out of the screen, basically to behind you, right? They want to point behind you. So I'm basically holding my right hand off to the side and kind of turning it so my palm is facing to the back so that my fingers can go from directly to the right to my back. And when I do that, my thumb is pointing downward. So this force is downward. Like that. Okay, so this guy right now is moving to the right, but it's going to feel a force downward. In terms of the acceleration, oh, by the way, and of course we could write FB is negative 1.28 times 10 to the 12th J newtons. If we think of, vertical as our J axis, up is positive J, down is negative J. So that would be like a a unified way of writing the magnitude and the direction using vectors. Okay, now acceleration. So this is just Newton's second law, so we can just do F divided by m. So the force we just found divided by the mass of a proton, which you look up, giving us 7.66 times 10 to the 14th meters per second squared. Okay, so and its its direction, because of course A is a vector too, would be in the same direction as the force. That's part of Newton's second law. The acceleration and the force are the same, so it would also be downward. So it would be negative 7.66 times 10 to the 14th J meters per second squared. That would be the acceleration. And one last thing before moving on, I realized that I kind of just reverted out of habit to 3 significant figures, but actually we only had 2 significant figures of input. So really my final answers should only be 2. So there we go. Okay. So that's a basic magnetic force problem, very basic.